we were going to title this talk, we would title it an application of multivariable functions to a person's purchasing of products in a two-bundle world or a two-product world. So we're going to assume that people are buying two products and they derive some level of happiness out of it. Okay, so we need to define the concept of what's called to be a utility function. So we're going to say let u of x comma y equal the utility, we'll say derived from a combination of quantities of two products, x and y. So I'm saying that there's this thing called the utility function, and it's derived from a combination of a quantity of two products, x and y. Utility is sort of a strange thing. It's a term in economics, but it's really supposed to be something that measures, we'll say, happiness, if that's something that can be measured. But how much utility does someone gain from purchasing a bundle of products? In the most abstract way, sometimes the units on utility is just called utils. So let's talk about what an example of utility curve might be. So let's pretend u of x comma y is equal to x to the 1/2, y to the 1/2. Okay, so this is an example of a utility curve. You could have written this as x y to the 1/2 power, the square root of x times y. If and x is the amount of, we'll call it the first product purchased, and then y is defined as a similar product. It's the amount of the second product purchased. That's what y is. So you can actually get a sense of the level curves of this if you want. So we'll draw an x and a y axis here. All right. And sort of the easiest way to think about the level curves is to just, let's fix the utility. So let's say for the minute that utility is equal to 1. If utility is equal to 1, that would imply that that x to the 1/2 times y to the 1/2 is equal to 1, or the square root of x times y is equal to 1. Okay, so you can start to think about some points that would satisfy that, right? So if we think about it, like, for example, 1, 1 would work. So if I had 1x and 1y, whatever it is, that would equate to a utility level of 1 unit of happiness. Okay, what else would work? Well, we could do, for example, maybe x was a fraction, right? Maybe this is something I can buy a certain percentage of, and then y is, I could buy over 100%. I don't know what it would be. Half of something I could purchase a half of, but half and 2 would work, so that would be up here, and then over here 2.5 would work. When I say 2.5, I mean x is 2, y is 1/2, and then 4 and 1/4 would work, and the square root of that's just 1, and so forth. So I end up with this thing here. So this is called a utility level curve. Okay, and in economics, what they would say is that any bundle you purchase along here, so if you decided to buy 4 x's and a 1/4 y, maybe these are things, like I said, we can buy by weight or something like that, 4 pounds of something, 1/4 pound of something else, then the utility I would gain out of that is equal to 1, whatever 1 means. And similarly, if I decided to buy 1 and 1, I would still get the same utility out. That's what this level curve is telling me. All right? So you could sort of think of this as like, this is a path I can walk along and maintain my utility, right? So you might say, how would you make a decision about where, what you would buy, right? Well, that's what we're going to get to eventually. So we'll work on that. If we reset the utility to a higher number, so for example, if utility was equal to 2, then that would imply 2 equals the square root of x times y. So that means that x times y is equal to 4. And by now, maybe you're realizing, hey, this is just that hyperbola that you graphed back in the 2D world. Okay? So what do we know? We go through 2, 2, and we go through some other points, and we end up with this utility level. This is utility level 2. And if we did 3, we would have it something like this, utility level 3. Okay? So these are called the level curves of our utility function. And they're exactly like a two-variable function that we've discussed when you have functions of x and y giving back z values. As a matter of fact, sometimes what they'll say is this is sort of like a hill of happiness, right? Here's what I mean by a hill of happiness. Imagine we started here at the origin and we started climbing this hill. If we headed it in this direction, we can see as we head in the direction of that black vector that we're getting to higher and higher level curves. Our utility's going up. So that's good, right? That's what we want to do. So sometimes what we say is that this thing's like a hill of happiness. You could graph this with a 3D grapher and see what this thing looks like. Yeah, and the question was, simply put, all right, well, just keep climbing the hill of happiness. But remember, x and y are products that we're going to have to purchase. So we're going to purchase those, and we're going to have some kind of budget constraint. And that's actually what's going to happen pretty soon. All right, but before we get to that, I need to go back to both through calculus for a minute and remind you of something called the total differential. Okay, so the total differential is a way to estimate small changes in z, and dz is equal to f sub x of x comma y times some small change in x plus f sub y of x comma y times a small change of y. Sort of what this is saying is that, say to ourselves, why would a small change in z be well estimated by this expression? My hint would be, look at each small contribution first. Way to envision why this works. So imagine here's our x-axis, and here's our y-axis here. And what we can do is we can start to sort of reason out why this must be true. So here we go. So we have some. Let's consider this. Okay, let's consider a box like this, and you'll see why I'm drawing the box in a minute. All right. So we're going to let this be here, sort of like we'll say this is sort of like my initial z value here. Right here is my initial z value. And my goal is this. Somewhere over here, I'm going to call this z1, and that's going to equal f of x1 comma y1. And there's an actual value there. If I know the function, I could take x1 and y1, sub it in, and get the actual z value that I have. What this expression above is saying is that if we have a certain slope in the x direction, which is what this represents, that's giving me a direction to head in. And then I have a small dx, which is this distance, dx, then my change, this slope times dx, would give me my change in y right here. Or my change in z, I should say. So this piece here, this change in z, now I should be careful. That's really the change in z that I'm getting as a result of x changing. So I could probably, if I wanted to, I could think of this as like partial f, partial f partial x, or partial z partial x, if you like that. And then what do I have to do with these two things? Well, I have to multiply them by the small change in delta x that I moved. And you can kind of see how, you could see how this would show you it's a small change in z. So this first piece here, this piece, is the change in z that we're getting from moving in the x direction. Okay? Now, the different color there, if I start from here now, right, at the top of this is the change I've experienced when x moved, then I can start to think, all right, well, what if I move in the y direction? Well, if I move in the y direction, if I move back delta y, there was a slope that I would experience. Okay? So this over here is a delta z, delta y contribution. So my picture's not perfect, but so I drew this rectangle so you can see I could take this line segment, this contribution to the change in z that x has contributed, and add it to back here. And now you can see the total differential. Hence the term total differential, because I'm adding the change in z contributed by x changing plus the change in z contributing by y changing. Okay, so having said that, we're going to go back to this example, and we can come to a nice, good definition for what are called the utility level curves. Okay, so that's what we're going to do. All right, now just a couple of things about notation. If you have a utility curve like this, u of x, y, then the first partial derivatives have special names. These come from economics. Well, not real, but other places, but economics too. We call this, the first derivative with respect of this thing with respect to x, you might think, oh, we call that ux. It's actually called mux, which stands for the marginal utility with respect to x. The marginal utility, okay, with respect to x. Okay, good. And then uy, if I took the derivative of this thing with respect to y, we usually call that muy, the marginal utility with respect to y. So these are the names of the first partial derivatives. What I'd like to do is take this notation and build an equation for utility level curves using the total differential, and that's what we're going to do now. So if we think about the picture I had drawn at the beginning of this whole story, here were our utility curves, and this was u equal to some fixed amount 1, here was u equal to 2, and so forth. So we had our utility curves. These were the paths we can walk along and stay equally happy. All right? What we know all along here is that the change, my d utility, is equal to 0. Right? Because my utility is not changing if I'm on a utility level curve. Okay? So now I'm going to put that together with the total differential. The total differential was dz equals fx delta x plus, or I should say dx, fy dy. In our case, we would have du equals marginal utility of x dx plus marginal utility y dy. Yeah, that's that. Okay, so we want this to equal 0 because I'm interested in coming up with a nice definition or something I can use that tells me something about the derivatives of these utility curves. Well, there you go. Utility is not going to change on a utility curve, so here we are. So what I'm going to do now is I'm going to solve this thing. Okay, we're going to solve for dy dx. So how do we do that? Well, we subtract this thing, negative mux dx, to the other side, and then we'll divide by negative muy, right? And then, well, whatever, it's all for it. So if we just do a little bit of algebra, here's what you get. You get dy dx is equal to negative mux over muy. Okay. So what we have now is an expression for the slope of a utility level curve with a fixed level of utility, right? So that's what we have. And you might say, okay, why do we go to the trouble of doing this, right? You know, you're doing all this. Okay, why? Well, because we're about to introduce what's called as a budget constraint to our situation. So I want you to keep this in mind for a minute, and then we're going to go back up here and look at this picture. Now, here's where things can get kind of interesting, all right? So let's pretend I have, this is x, this is y. So let's pretend I have a certain amount of income. I have a certain amount of money I'm able to spend on these two products. Now, P sub x is going to be the price, I should say the unit price of x. And we're going to let P sub y equal the unit price of y. So what do I know then? Well, I know that the amount of x I buy times P of x, the price per unit, plus the amount of y I buy times P of y, which is the price per unit of y, must be less than or equal to my income. Okay? That's called a budget constraint. All right? So what do we know then? Well, we know that this thing is linear, and its graph would end up looking something like this. If x and p of x and y and py are all positive, right, it's less than this, the graph is going to do something like that. Okay? And we actually know some special points. For example, this point here means I decided to buy only x, right? Y is equal to 0 all along this line. So this point would actually be, this is I divided by P of X. This means you bought this is as many X's as you can buy. You took all your income, you divided by the price you spent for each unit of X. And then in a similar fashion, this is I divided by P of Y. Sort of a theorem, and we're not going to glance over why it's true, but if we think about buying stuff along bundles along this line, a question you may ask yourself is, hey, can I just buy any bundle of X and Y? Can I just spend all my income on any combination of X and Y and be equally happy? Well, I ask that. Reminders. Remember, any combination on these utility curves gives us an equal level of happiness. Okay? Now, if you think about it, here, this point up here, for example, right, that's a point that's above my budget constraint. I can't even afford to buy that point. But I'm not worried, because I can afford to buy that point, and that point makes me equally happy, right? As a matter of fact, I can afford to buy all the points on this section of a curve, because they're below my budget constraint, and be equally happy. So the question is, what bundle XY should I buy? Should I buy this one? Should I buy this one? What might be true if I bought one in between? There are other utility curves that I haven't drawn, but there is a utility curve between these two, and we know that the level of utility there is higher than 1 but less than 2, so maybe it's 1.5. There's also a utility curve that'll come by and just skim and be tangent to the budget constraint. So here's a little theorem for you, a little thing to think about. The maximum level of utility I can attain when the utility curves are, I should say, we'll say this, they look like they're concave up in the xy plane. When they're concave up in the xy plane, happens when the budget constraint is tangent to a utility curve. That would get me to the highest possible level of utility. So I made a very important, I mentioned the word concave up in the xy plane. Keep in mind, if we had utility curves that for some reason looked like this, and then we impose a budget constraint on things, then you would see, to get to the highest level of utility, you'd want to buy maybe this bundle, right? Because that's getting me to the highest level of utility. And the picture that I've drawn, the way utility curves are, you can see they're convex with respect to the origin, or they were concave up in the xy plane. I'm looking for the point of tangency, or the point where the following happens. The slope of the budget constraint equals the slope of the utility curve. So that's what you're looking for. Okay? So we could do that for an example. So let's do it for an example. So let's consider the following. Let's consider our hypothetical example. U of x comma y is 1/2, x to the 1/2, y to the 1/2. And we have the following facts. The price of x is 3, the price of y is 4, and our income is 15. So this implies that this is the budget constraint we got to live with. 3x plus 4y is less than or equal to 15. For those of you who get nervous saying my income's only 15, keep in mind this is the money that we've decided to spend on products x and y. It might not be our total income. Okay? Another way to think of this is y is less than or equal to 15/4 minus 3/4 x. Okay. Now, what do we know? Well, based on the picture we had, we know we're looking for the point where the slope of the budget constraint is equal to the slope of the tangent of the utility curve. And we already know how to get the slope of the tangent utility curve right here. Here it is. So all we got to do is go find that. So let's do a little bit of work here and see what we have. Well, the marginal utility of x. And we think of the utility, here it is. Here's that utility curve. If x is the variable, then y to the 1/2 is a coefficient. So you have y to the 1/2 times 1/2 x to the negative 1/2. That's the marginal utility with respect to x. All right, and then by symmetry, you get this, right? Now y is the variable, x to the 1/2 is the coefficient, and then you end up with 1/2 y to the negative 1/2. Okay, so we can simplify things a little bit. So what is this going to happen? Remember, the slope of the utility curves is negative mux over muy. We would not have known that had we not taken the differential for utility and set it equal to 0. So that's the whole premise of where this comes from. Okay? Because we're trying to find the slope of a constant level of utility. All right, so what is this going to equal? Well, we can sub all this stuff in and see what we get if you want to do that. Let's see. We have negative mux. So it's going to be y to the 1/2, 1/2 x to the negative 1/2. And there's a negative in front because of that negative. And on the bottom, we have 1/2 x to the 1/2, 1/2 y to the negative 1/2. And then a little bit of algebra. Well, the 1/2s cancel. The x to the negative 1/2 is going to come down into the denominator. The y to the 1/2, negative 1/2 is going to come up to the numerator. And you're going to get the following, that negative mux over muy is equal to negative y over x. That's what you get. So this is the slope of your utility curves. By the way, just as an interesting fact, sometimes this thing here, the slope of the budget constraint, is called the marginal rate of substitution, the MRS. You might see that. All right. So what we got to do now is just set that equal to the slope of the budget constraint. So negative y over x has to equal the slope of the budget constraint, which we said was negative 3/4. There it is. You can see it when you write the equation in y equals mx plus b form. So negative 3/4. So that implies that 3/4 of x is equal to y. Well, now I can figure out the optimal bundle. If this holds true, I will find a point where I'm on the budget constraint, and that point on the budget constraint has a slope. I'm sorry, well, I should say this. That point on the budget constraint it has the tangent line to the utility curve would be parallel to the slope of the budget constraint there. It's a lot to say, but whatever. Okay, here we go. So all you have to do is take the budget constraint. Here you go. We're going to spend all our income here. And 3x plus 4 times 3/4 of x is equal to 15. All right, so if we solve that, we're going to get x equals 15/6. So we have to buy that much x. And then y equals 3/4 of that. So we get 15/8. So what you say is the bundle 15/6, 15/8 is the optimal bundle for this person to purchase to maximize their utility.